In this question, we're going to deal with an ICE table where we know the equilibrium constant, but we don't actually know the equilibrium value of any of the chemicals. So this says in a 500 milliliter stainless steel reaction vessel at 900 degrees Celsius, carbon monoxide and water vapor react to produce carbon dioxide and water, or hydrogen. The evidence indicates this reaction establishes an equilibrium with only partial conversion of reactants to products. Initially, 2 mole of each reactant is placed in the vessel. So 2 mole in a 500 milliliter vessel, so you've got 2 mole divided by 0.5 liters, is going to give us 4.00 mole per liter of each of the reactants. So those are each put in the vessel, and these are 0, right? Initially, 2 mole of each reactant is placed in the vessel. Kc for this reaction is 4.20 at 900 degrees Celsius. What amount of concentration of each substance will be present at equilibrium? So this is all it's told me, that its Kc is 4.2, and it gave me the initial conditions. But I know that if I calculate Kc, it's the products raised to their coefficient, so 1, times the hydrogen raised to the power of 1, divided by carbon monoxide gas divided by to power of 1, and water vapor to the power of 1. So this is my Kc expression. Since I know this number, if I could fill these blanks in, I could probably figure it out. Now, whatever this is that's being made is going to increase by x, and this would increase by x, because it's a 1-to-1 ratio. Those are reasonable assumptions. So I'll make x. But if I'm going to make each of these, and it's 1-to-1, this is going to cost an x here. So this is times 1 over 1, so it's minus x. So this is 4.00 minus x times 1 over 1. So it's minus x. This is 4.00 minus x. So both of my reactants are going to be decreased by x, and I'm going to produce x in my products. So my Kc, which is 4.20, will equal x times x over 4.00 minus x times 4.00 minus x. So this equals x squared over 4.00 minus x. Well, I can find the relationship here if I could take the square root of 4.20 and the square root of x squared and the square root of 4.00 minus x squared. I can calculate what the value would be. So the square root of 4.20 is 2.05. You have to do that in your calculator. And then that's equal to x, which is the square root of x squared, divided by 4.00 minus x. At this point, I'm just going to try to solve for x. So I'm going to multiply this by this side, so I get 8.10 minus 2.05x equals x. That's just taking this and multiplying both sides by it, right? And then I'm going to group my x's. So I'm going to take this to this side, and I get 8.10 equals 3.05x. I have to add 2.05x to each side. And so x equals 8.10 divided by 3.05. And we get the value for x from that. So I've got 8.1 divided by 3.05, and it is x equals 2.66. And I can take that value and substitute it in here. So I know that the value of x is 2.66. So this is 2.66. And that this will be 4.00 minus 2.06. So that's going to be, or pardon me, 2.66. So this is going to be 1.34, and this will be the same number because it's 4.00 minus 2.66. And I've got the mole per liter concentration for all my reactants and products at equilibrium. And I've just done some algebra to get there. The maximum possible yield for this would have been 4.00, because if this had made this, it would have been 4.00. If this had made this, it would have been 4.00, because it's a 1-to-1 ratio and they're the same amount. So your percent reaction is going to be 2.66 divided by 4.00 times 100%. And that gives me 66% forward reaction. And so it favors the products. So if we get into a situation where you're given a KC and only the starting amounts of chemicals, if we set up our ICE table so that the difference is X, we can then substitute those values in and calculate the equilibrium concentrations.